Okay, in this lecture, let's continue to talk about simple linear regression. So, the main focus of this handout is to study the relationship between two quantitative variables, x and y, right? So the first step, we are going to collect data, and data is usually in form of pairs of observations x1, y1 to xn, yn. After we got the data, the first step, we are going to draw a scatter plot like this to take a look at how does this data looks like, get a feel of the data. And if this data scatter plot looks linear, which we may think is pretty reasonable for us to find a linear line as the best description of the pattern of the data, then we will go ahead to do the simple linear regression, which is we are going to find the best fitted line between the variable x and the variable y. Usually the variable x will be the explanatory variable, and the variable y will be the response variable. We are using the explanatory variable x to explain the variable y, so we use x to estimate y, or we use x to predict y. So the first step, we are going to draw a plot, a scatter plot, to see if there is any linear relationship. If there is, then we will go ahead to fit a linear model, which is a straight line model. So a straight line, I think you have learned that from your high school. We usually, this is what you use in high school to describe a straight line, right? Here we are going to use a different parameter. It's the same idea, just the parameter is going to be different. So we use y equals to beta 0 plus beta 1x. So here, this y is our true y, and those beta 0 and beta 1 is our true x. Because those are random, so this y will not be beta 0 plus beta 1x. There may be some random error here, and we use this epsilon to denote any random error. It may be associated with this line. So in this simple linear regression model, this beta 0 is called the intercept, beta 1 is called the slope, and those are the true parameters. Those are the true parameters. And this epsilon is the random error. And our x is fixed. And in this model, we usually will call y the response variable, or the dependent variable, or outcome. We usually will call x the explanatory variable, or independent variable, or predictor. Now we know this y equals beta 0 plus beta 1x plus epsilon is going to be the fitted is going to be the true model that we are trying to look for, then how could we find the best fitted line here? So those beta 0 and beta 1 are the true parameters. If we use our data to find the best fitted line, then the beta 0 hat and beta 1 hat that we got from this our data is called estimated or it's our fitted parameters. So beta 0 and beta 1 are true parameters. Beta 0 hat and beta 1 hat is fitted or estimated parameters. And the idea we use to find our best fitted line is called least square estimation. Okay, so what is least square estimation? The idea is like this, suppose we have 4 data points. Again, the first, you're going to draw a scatter plot and you see 4 data points like this. You want to fit a line that's best describe the relationship between x and y, best describe the pattern, the linear pattern of those data. So how do you decide which one will be the best fitted line? So, okay, you may think, okay, this is the best fitted line, and maybe the other students think this is the best fitted line, while your professor draw this blue line as the best fitted line. Which one do you think is the best option? We will say this blue line will be the best option, not because this is drawn by your professor, but because it minimizes the error, or the square errors, or so the residues. So suppose this is the best fitted line, and those red points, they are the real data. They are the real, they are called observed values. So this is the observed value. The value on this fitted line, say when x equals to 3, this is our fitted value. Because this line is our fitted line. So the value on this is our fitted line. So the value on this line is called fitted value. The difference between the fitted value on the line and the actual observed data is called residues or errors. So let's just use residues to denote it. So this residue will be the actual true observed value you got from the data minus the fitted value on the line. Please note that you can't exchange the order here. The residue could be positive and could be negative. So it's always going to be the observed value minus the fitted value. Now we want to find a line where those points are as closer to the line as possible. That will be the best fitted line to describe the pattern of the data, right? So we want those lines to be as closer to this line as possible. So how to make those, residues small? How to find a line that will make those residues small? The first idea is maybe, okay, we can sum all those residues together to see which one has the minimum number, right? We try all those different lines, like what I just draw, and then I erased it to see which one has the smallest sum of residues, right? This is a good idea, but there is a problem with this idea is because those residues could be positive and could be negative. If you sum them all together, it may be close to zero. So you may get a line which has the very small sum of residues, but actually the points are not clustered around the line. Points are pretty far away from the line. It's just happened to sum up to be close to zero because it has positives and negatives and it cancels off each other. So we want to square it. We want to minimize the square of those residues. And that's why it's called least square estimation. We want to find a best fitted line where the squares of the residues could be minimized. Then how could we find such line that the squares of the residues will be minimized? Recall that this best fitted line is the fitted line of our true model y equals to beta 0 plus beta 1x, right? Then that's the true model. The fitted model will be yi equals to beta 0 hat plus beta 1 hat xi. That is your y beta 0 hat and beta 1 hat are the fitted parameters the fitted estimates that we got from our data, and when we plug in those beta 0 and beta 0 hat and beta 1 hat into that true model, we will have this y hat. So this is the fitted line. This is the fitted line. So this y hat equals to beta 0 hat plus beta 1 hat xi. This is this line. This is this line here. And because it's the estimates of, this is just this line, so we don't have any random error epsilon associated with it. Now we are trying to find the minimum of this. Now let's continue. We are trying to find, say, let's use L to denote the sum of residues, which is yi minus beta 0 hat and beta 1 hat xi squared. Remember, this is your yi hat, and you sum all those residues together. This is the sum of residues. We want this to be minimized. How do we find the minimum of something? We have two parameters, beta 0 and beta 1, that we want to solve, right? In order to find the value of beta 0 hat and beta 1 hat that will make this L to be minimal, what we do is we do this, right? We set this equals to 0, and this equals to 0. To solve those simultaneous equations, we are going to have a solution like this. So I'm going to skip the steps that we are going to use to solve this. The solution is this. This is beta 1 hat. It's going to be like this. And the numerator, we use sxy to denote it. The denominator, we use sxx to denote it. And this beta 0, 1, beta, this is beta 1 hat. And this is beta 0 hat. This is y bar minus beta 1 hat times x bar. The beta 1 hat will be, so we have an estimated regression line. And the beta 1 hat is the slope. The interpretation of the slope, that is, for 1 unit of change in x, there will be beta 1 hat unit of change in the mean of the y. So this is change in the mean of y when x changes 1 unit. While the beta 0 hat is the intercept. That is the mean of y when x equals to 0. There is also another thing I would like you to take a look at. This is the formula for beta 1 hat and beta 0 hat. You don't really need to remember all those formula, but there is one thing. Take a look at this formula and take a look at the formula for the R, the correlation. What do you notice? You see that the numerator are the same and the denominator are always positive. So we can actually see that this beta 1 hat is having the same sign as the correlation, right? Which is pretty reasonable to understand. If the slope of your fitting line is positive, that means x and y is having a positive linear relationship. If the fitted slope of your line is negative, that means your linear relationship between x and y is negative. So beta 1 hat and the R is having the same sign.